In section 13.4, we begin to do some quantitative equilibrium calculations, and importantly, we establish the concept of the reaction table or the ICE table. This is going to be something that we'll be using again and again throughout the quarter. So in complex equilibrium problems, concentrations of some things might not be known, and the easiest way to solve these kinds of problems is to construct what's referred to as the reaction table, or a lot of people will call it an ICE table. So how you make the ICE table is on the top line of your table, you put your chemical equation, and it's always going to be an equilibrium calculation. You can do it for non-reversible reactions as well. It's important to record the units that you're going to be working in, because we don't want to be doing a Kp calculation when really we should be doing a Kc calculation. So that will be either ATM or molarity will go in there. And then you'll write the letters I, C, E. The I stands for initial, which is going to be your initial pressures or concentrations. Then there will be a change occurring as the system comes into equilibrium. Some things will go down, some things will come up in concentration, and then finally you'll arrive at your equilibrium position. So let's just have a look at a few examples here. So this is example: solid graphite that has been heated to 1080 K is reacted with CO2 at an initial pressure of 0.458 atmospheres. So this is 0.458 atm to begin with. Okay, and then it says the system is allowed to come to equilibrium, at which time the total pressure is 0.757 atm. What is Kp? So to begin with, we're going to set up the ICE table. So we put our equation across the top. We've made note that we're working in atm, and then we put in our initial pressures in atm. So initially we have 0.458 atm of CO2. We don't need to worry about the pressure of the carbon, because it's a solid. It's not going to be part of our equilibrium calculation. So we've just put the dashes there to indicate that we're not going to be bothering with that. And then there's no mention of the CO being present initially, so that concentration must be 0. So what way does the equilibrium move? Well, it can't move to the left because we don't have any CO. It has to move to the right. So this is going to go down by some amount x. And because for every one CO2 you make 2 COs, the CO must go up by some amount 2x. So when the system comes to equilibrium, the equilibrium amount of CO2 will be 0.458 minus x, and the equilibrium amount of CO will just be 2x. So what we have to do now is figure out what x is, and that's generally what we're going to be working to do on most of these ICE table problems. So they gave you a little bit of a hint. They said that the total pressure is 0.757 atm when it comes to equilibrium. So that means if I take this and I add to it the 2x, the total will be 0.757 atm. So I can solve now, right, for x. So the total pressure is the pressure of the CO2 plus the pressure of the carbon monoxide, and that equals 0.757. The CO2 has a partial pressure of 0.458 minus x, and then the CO has a partial pressure of 2x. So not too bad. I can do this. 0.757 equals 0.458 plus x, because that's just going to cancel out, isn't it? And then reorganizing and solving for x, and x equals 0.299 atm. So now I go ahead and update my bottom row of my ICE table, and I did my 0.458 minus my 0.299, and that gives me my pressure in atm of my CO2. And then my CO went up by 2x from 0, so 2 times 0.299, it gives me 0.598. And so now my Kp is going to be my partial pressure of my CO squared, 0.598 squared, over my partial pressure of my CO2 at equilibrium, 0.159, and I got an equilibrium constant of 2.25. So that's kind of telling me that's kind of one of those intermediate ones. It's not really, really tiny and it's not really, really big. So I've got a mixture of reactants and products. You can see that we just basically ignored the carbon because it was a solid. A common type of problem where you'll use an ice table is when you will be given an equilibrium constant and some initial concentrations, and what you're hoping to find out is what are the equilibrium concentrations. So in this example, you're told that this reaction here, it's got a Kc of 1.56. So what we're thinking is it's probably going to have a mixture of reactants and products. Perhaps it's mostly reactants and only a little bit of products. So this reaction occurs at 900 K. They're just telling you that it's at constant temperature. They give you the value of Kc. And then it says that carbon monoxide and water are combined in the same vessel to give initial concentrations of 2 moles per litre and 1 mole per litre. So what that means is that when we start, we're just kind of mixing reactants together. We don't have none of those at the beginning, okay? We just have these guys, and it looks like that's 2 molar and that's 1 molar, okay? And then the question is asking, what are the equilibrium concentrations of these two components, so the CO and the water at the end? So, you know, like here, where do I begin? So let's kind of set up the reaction table and then see if we can work through it from there. So we wrote our reaction out. We're working with a Kc, so we're going to be working in molarity. And initially we had 2 moles per litre of the CO and 1 mole per litre of the water vapour. We had none of the CO2 and none of the hydrogen. So it can't be moving to the left. It's going to have to be moving to the right. It's not possible to move to the left because we don't have any products. So what's going to happen is the CO will go down by some amount X, the H2O will also go down by some amount X, the CO2 will go up by X, and the hydrogen will go up by X. And it's X for all of these guys because it's a 1 to 1 to 1 to 1 ratio. So when the system comes to equilibrium, we'll have 2 minus X moles per litre CO, 1 minus X moles per litre H2O, X moles per litre CO2, and X moles per litre H2. So here's my expression for Kc. It's just products over reactants, and it's nice and easy because everything is 1. Okay, so now I'm going to start putting in my concentrations that I have, and I'm going to put them in terms of what's present at equilibrium because we're after an equilibrium constant. And so we've got X moles per litre for the CO2, X moles per litre for the H2, so that's going to give me X squared. And then this guy is 2 minus X moles per litre, so that's that term there. And then this one here is 1 more, the minus X moles per litre there. Now, if I can use the solver, at this point I'm done. I'm just going to put this expression into my solver and I'm going to solve for X. If I am absolutely determined not to use the solver, then you're in for a world of pain. So what you have to do at this point is distribute the bottom line, make sure you don't make an error, and that will give you this expression here. And then what we're going to do is we're going to collect everything on the one side. So the first thing I'm going to do is times everything by what's on the bottom line on both sides. So that will get me to there. And then I've got to distribute this, which is what I've done there. And then I've also brought over the X squared so that it equals 0. And then I'm just going to collect these like terms, these X squared like terms. And so that gives me this expression. And you can see that this is a quadratic equation of the form AX squared plus bx plus c equals 0, where we've got a equals 0.56, b equals minus 4.68, and c equals 3.12. So if we have a quadratic expression, we can use the quadratic formula to solve for what x is. As I pointed out, everything is done if you know how to use the solver. Once you get to that point, you don't need to do this. So here's our quadratic expression here, and these are our parameters a, b, and c. So now we have to use the quadratic formula to solve for x. So we have this term, this is our quadratic formula, and we what I normally do is evaluate the square root term first, and then take it from there. So we ended up with you always end up with two possible solutions to the quadratic formula. We've got 0.73 molar or 7.6 molar, and we have to decide what one is correct. What will happen is one of your solutions will not make any sense. It won't be physically possible. So if we look at our ICE table, that can help us decide what one is the correct answer. So considering we only started with 2 moles per liter and 1 moles per liter there, so the 1 mole per liter of H2O is our limiting reactant, the maximum amount of CO2 or H2 that we could create, the maximum value for X would have to be 1, and that would be if we turned all of our H2O into product. So when you consider that, the only solution to the quadratic formula that makes any sense is this one, because the other one was more than 7, and that's just not possible. So now we go in and we update our ICE table with this value of X. Here it is here, and now we've got our equilibrium concentrations. Okay, so that's using the quadratic formula to solve for the equilibrium concentrations. It's not always necessary. It's kind of unusual that you need to use the quadratic formula. Sometimes we don't have a situation where we have 100% reactants or 100% products. We have a mixture of reactants and products in our initial state. And if that is the case, we'll need to solve for Q first in order to know what the direction of change will be. So in this problem, it says the value of Kc for this reaction here, N2O4 in equilibrium with 2NO2, is 0.21. So it probably favors the reactants. It says if a reaction vessel initially contains 0.03 molar NO2 and 0.03 molar N2O4, what are the concentrations of the two gases at equilibrium? So in this case, we've got some reactants and some products. So we can't make any assumption about what direction it's going to shift. So what I'm going to do is set up the ICE table, and you can see we have equal amounts of the N2O4 and NO2 to begin with. And then I'm going to calculate Q, and I'm going to compare it to K. So it's products over reactants, but we've got to square the products because there's 2 of them. So it's going to be 0.03 squared divided by 0.03, and that's just going to be equal to 0.03, and that is less than our K, and our K was like 0.2. So that's a lot less than K. So when Q is less than K, that tells us that our reaction is going to shift towards the products. So what's going to happen is that our N2O4 will go down by some amount X, but our NO2 will go up by some amount X because we've got 2 NO2s here. So when it comes to equilibrium, our amount of N2O4 will be 0.03 minus X, and our amount of NO2 will be 0.03 plus 2x. So now I put that information into my expression for K, and I solve for X. So here we go. It's products over reactants. So there's my products line. I've got to square it. Here's my reactants line, and that equals 0.21 according to my information that was given. Now again, if you use the solver, you're done at this point, okay? And when we use the solver, we know that the maximum possible value for X would be 0.03, and that would be equivalent to all of our reactant being turned into product. Yeah, that's the maximum possible value for X. Okay, so we're going to pretend we don't know anything about the solver. So the first thing that we're going to have to do is we're going to have to multiply both sides by the bottom line, which is what's happening here. And then we're going to have to square the top line, which is what's happening here in this part there. Square the top line and sort of distribute all of that. And then we're going to bring everything onto the one side. So we have an equation that equals 0. And you can see it's getting pretty ugly because we have these really weird numbers here. And then we have to collect the like terms. So we've got to collect the x terms. And eventually we end up with an expression that's in the form of a quadratic. My a is 4, my b is 0.27, and my c is minus 5.4 by 10 to the minus 3. So then I put that into the quadratic formula, and I get my 2 roots. And remember that only one of these values is going to be sensible. So we've got minus 0.084. That doesn't make any sense. There's no way that this can be, our change is not going to be a minus, because that would be equivalent to the N2O4 increasing. So that doesn't make any sense. Plus it's bigger than 0.03. It's got to be that one. Okay, so a lot of work if you're not going to do the solver. Okay, so now at this point we update our ICE table to get the concentration of N2O4, so 0.030 minus X, minus 0.016, and then there's our equilibrium concentration, or equilibrium, yes, concentration, because we're in molarity, of N2O4. If we want, we can go through and calculate the equilibrium amount of NO2 as well. All right. So is there anything we can do to make these calculations a little easier? And there is. Sometimes K is really small. You know, like by small we mean like sometimes it's like even less than, 10 to the minus 5. And the consequence of that is that the concentration of the reactants, they change by a very small amount, like 5% or less. And if that is the case, if the change in the concentrations is less than 5%, then that's going to be really negligible and we can actually neglect it. So I'll give you, and it doesn't have any impact on the answer. So I'll give you an example of this. We will know that this is, appropriate to neglect the change in concentration of the reactants when we have a really small K. And you can kind of check that using this little formula here. You take your initial concentration of your reactant and you divide it by K, and if that is greater than 500, you're probably going to see a less than 5% change in the concentration of your reactants, and you can go ahead and safely kind of neglect how they are changing. So here we've got this reaction. The value of Kc for the reaction, and it's COCO2 in equilibrium with CO and Cl2, is 2.2 by 10 to the minus 10. Now that is very small, right? So basically, it's going to really favor the left-hand side. It says if a reaction vessel initially contains 0.03 moles COCl2 and 0.03 moles of Cl2, what are the concentrations of the three gases at equilibrium? So we want the concentration of everything. So to begin with, we have a little bit of Cl2 and a little bit of COCl2, but no CO. So our ICE table looks like this. 0.03 moles per liter of this guy, none of this guy, and 0.03 moles per liter this way. Because we have none of the CO, we know that the equilibrium can't move to the left. The equilibrium has to move to the right because there just isn't any CO to react. So what's going to happen is that the COCl2 will go down by X, the CO will go up by X, and the Cl2 will go up by X. As this is an itty bitty concentration here, K here, it's really, not going to move a lot towards products. And so what we're going to say is that the equilibrium concentration of our reactant is pretty much the same as what it was to begin with, that X is just going to be so itty bitty, that X is going to be less than 5% of that number there. We're going to say that our CO will go up by some amount X, but we're aware that X is going to be very, very tiny. And then our Cl2 will also go up by some amount X, but x is so tiny that at equilibrium, the amount is going to be about what we started with as well. So what that means is that Kc is approximately equal to x multiplied by 0.03, that's our products, divided by my equilibrium concentration, my reactants, 0.03. You can see the 0.03s cancel out, and that gives me x. So I'm done, right? So x is approximately equal to my my Kc value, and my Kc value was 2.2 by 10 to the minus 10. Okay, so what do I know? The concentration of my CO and my COCl2, sorry, my COCl2 and my Cl2 will just be 0.03, and the concentration of my CO is 2.2 by 10 to the minus 10. Now, if I used either the quadratic formula or the solver to get the exact answer, when I express things to the correct number of significant figures, I get identical answers. So this is really good. You don't have to learn how to do the approximation, but it avoids a lot of really awkward math, and I really like doing the approximation, and you can do it for a significant number of problems. It really speeds things up. Okay, so I would